Good day to our lecturer, NJMD Nur Anwar bin Muhammad. My name is Anil Khajan Koshi, and our group, which is Group 2A from Section 2, will be doing our video presentation on our open-ended experiment, which is the two-stage air compressor. So for the introduction of two-stage air compressor, a two-stage air compressor is a type of compressor which compresses air in two stages. It increases the pressure from lower pressure to a higher pressure level by reducing the volume of gas and completely making the gas pressure and temperature increase. A two-stage air compressor has two cylinders, and each cylinder has a piston where the fluid compresses two times. One of the piston is used for compressing the air, while the second piston is used to transfer the compressed air from one cylinder to another. A two-stage air compressor usually has two air storage chambers and two pistons for pumping air. At the first stage, air is drawn in and compressed to an intermediate pressure. After being compressed in the first stage, the air is piped through a heat exchanger where the intermediate air is allowed to cool down and then compressed in the second stage. Furthermore, there is an aftercooler in the two-stage compressor that works to reduce the temperature of air and remove moisture from the air. For this open-ended experiment, we will study the two-stage air compressor and do analysis and further study based on experimental data. So this is the schematic drawing of two-stage air compressor. And for the objectives of the experiment, the first objective is to understand the polytropic process of two-stage air compressor. The second is to determine the polytropic efficiency of two-stage compressor. And lastly, to determine the heat loss from the system. So next, for the theory of the two-stage air compressor. The air compression in the air compression in a compressor usually undergoes a polytropic process in the form of PV power of n equal to C, where n is the polytropic coefficient. We assume that the mole air is considered as ideal gas with the characteristic equation PV over T equals to constant. Then, useful relationship between the temperature and pressure or temperature and volume for any point during the process can be obtained as follows. From equation 1, PV power of n equal to C, then we will get P1V1 power of n equal to P2V2 power of n. And the property of ideal gas follows the equation PV over T equals to C, which forms equation 2. And we will get P1V1 over T1 equals to P2V2 over T2. And from equation 2, it yields T2 over T1 equals to P2V2 over P1V1. And substituting this together with equation 1, we obtain T2 over T1 equals to bracket P2 over P1 power of n minus 1 over n, which forms equation 4. Index 1 and index 2 refers to the air condition at inlet and outlet of the compressor respectively. So for the next part of the theory, we will be talking about the work and efficiency. The work required to compress the air from the initial pressure P1 to the delivery pressure P2 is given by equation 5, where W indicated equals the integration of P2 P1 V dP, which forms equation 5. By substituting equation 1 into 5 and using the ideal gas equation, the equation of indicated work can be obtained as shown below. So Win equals to n over n minus 1 times P1 V1 bracket P2 over P1 bracket power of n minus 1 over n minus 1, which forms equation 6. For the two-stage compressor, the total work done on the system is the sum of the work done by each compressor. Between work and polytropic power, PP, the relation is given as PP equals to m dot times Win, which forms equation 7. Equation 6 is substituted into 7 And using the ideal gas equation, we will get Pp equals to n over n minus 1 m dot r1 t1 bracket p2 over p1 bracket power of n minus 1 over n minus 1, which forms equation A. The polytropic efficiency of compressor NP equals to Pp over Ps, where Ps is the motor shaft power. To produce Ps, the compressor requires electrical power, Pe. Therefore, efficiency M equals to Ps over Pe, where Nm is the motor efficiency and Np is 98%. And M is 80%, which can be used for in this equation. So next, for the heat loss in heat exchanger, the heat produced in the air compressor is rejected into the heat exchangers. The total heat absorbed by the cooling medium, which is water, can be shown in equation 11. Q equals to Q1 plus Q2, and Q equals to M dot bracket H out minus H in 1 plus M dot 2, H out 2 minus H out 2, H in supposed to be H out 2 minus H in 2. So applying this equation to the compressor, it becomes Q equals to M dot 1 bracket H8 minus H7 plus M dot 2 bracket H9 minus H7, which forms equation 12. For M dot, use M dot equals to rho W, where rho and W is density and the mass flow rate of water respectively. And next, we will be talking about the heat loss in the compressor. From the first law of thermodynamics, the energy balance per mass in the compressor with an assumption that kinetic and potential energy changes is negligible at the equation below. So we have equation 13 where Q minus W equals to delta H, and we rearrange this equation. The heat loss per unit mass in each compressor can be obtained as below. Q equals to delta H plus W, which forms equation 14.
Assalamualaikum, and today I will presenting about procedure for two-stage compressor. So first, make sure the flow rate of cooling water is sufficient, approximately 100 per H. Adjust it using the valve, then connect the water inlet and outlet properly. Second, plug in the flexible cable into the diagram D1 for compressing air at D4 2.5 bar absolute. So next, start the car compressor by turning on the main switch on control panel. Then record the data for section condition into the table data sheet, then wait for about 10 minutes to get a steady table condition. Next is record the valve for temperature and pressure as indicated in the column first stage compressor of the data sheet, and wait again for 5 minutes. Number 6 is fill up the valve in the column second stage compression and wait 5 minutes for the final compression. Next is number 7, record the rest of data in the data sheet. 8, repeat the 1 until step 7 for P4 4 bar and P4 7 bar absolute by replacing for cable flexible into diagram D2 and D3. Next, I will present about the result experiment. So first we have a pressure, ambient air, and first stage of compression, then second stage of compression, and final compression. So pressure we have P4 2.5, 4 and 7. Ambient air we have TO, PO. With the data, first stage compression, as we can see, we have T1, P1, T1 to TO, P1 to PO, T1 per TO, and B1. Next is second stage of compressor. we have T2, T3, P2, T3 minus T2, P2 minus P1 and 3 per T2, PT per T2. Final compressor we have for T4 and P3. Next is next result, we have a pressure, temperature, water circuit, air flow rate, input power, tank, exchange water inlet, exchange 1 water outlet and exchange 2 water outlet. At pressure we have P4, and as we can see the pressure is 2.5, 4 and 7. Second tank temperature we have T5. Water circuit we have W1 and W2. Air flow rate we have V. Input power we have PE. And then air tank we have T6. Exchange water inlet we have T7. Exchange 1 water outlet we have T8, and exchange 2 water outlet we have T9. So that's it for my presentation. Thank you.
An observation: when the water flow into the compressor through the piping system, the reading of water flow exchanger 1 and 2 must 100 LOH. In this experiment, the P4 takes a long time to achieve constant value. Other than that, it takes 10 minutes for first state before the reading was taken, another 5 minutes each to take the reading in second state and final compression. When the P4 at 7 bar, the compressor will stop a few moments because of the compressor need to release some air, but the compressor does not need to switch off because of the operate back to normal.
Hello and good day. My name is Selvin Budipes Barau, and I'm going to present about the discussion. So the first question is: draw the curve Q1 equal to F beta 1, where beta 1 is equivalent to P1 over P0. So in here, there's a formula we use to calculate in order to find the Q1, which is Q minus M times H2 minus 1, and then we calculate the M1, which is the formula is the density times W, where we get the M1 is 0.0278 for both M1 and M2. And then as for the pressure 2.5 bar, where we obtain the temperature as well from the data as we did the experiment, which is 29.8 degrees C. In order to find the H, where the H is the enthalpy for temperature 7, and then we find the enthalpy for temperature 8, where we get the H 8 is 159.591 and the same goes to the temperature 9. We get the enthalpy is 143.296 kilojoule per kilogram. And then after we get all the enthalpy, we substitute all the enthalpy into the equation, which is for the Q1 equal to 0.278 times 159.5918 minus 124.9016, and we get the answer of 0.9643 kilo per second. And then from this table, after we calculate the data, and then we convert the data into this table in order to draw the curve, where the curve is increasing, and this is the curve for graph Q1 versus, against beta 1. And for the question number 2, we calculate the Q2 and beta 2 as the same as the question number 1. So we convert this table into this graph, where is a little bit almost perfect curve. So I guess that the activity or the experiment is achieved. So next, as for the question number 3, calculate the polytropic coefficient, which is n, for this two-stage air compressor. So this is how we calculate by using the formula where the T2 over T1 equivalent to pressure 2 over pressure 1 to the power of n minus 1 over n. So, and then for the F4, which is 2.5 bar, we already know the temperature for the T1 and T2, and it's the same as well as pressure 1 and pressure 2, 1.8 bar from the table from the data we collect from the experiment, and then we calculate this by using the given formula in order to get the n value, which is for the pressure 4, which is 2.5 bar, the n value is 0.537 watt. And as for the pressure for the 4 bar, we obtain the n value is 0.7480. And then lastly, as for 7 bar, we obtain the n value is 0.190 as for the polytropic coefficient n for this two-stage air compressor. So we find the n value at the previous slide. Then we calculate the polytropic work for each P4, which is 2.5 bar, 4 bar, and 7 bar. So how we calculate the polytropic work? There's a formula which is the polytropic power, which is equivalent to n over n minus 1 times m times the ideal gas constant value, which is we can obtain from the table A2. And then T1 is already obtained in the table, then times with pressure 2 and pressure 1 to the power of n minus 1, and then over n and then minus 1. So as for the 2.5 bar, we already calculate the n value, and the ideal gas for air, which is refer to table A2, we get the 0.2870, and then substitute all the equation, all the number above, and into the formula in order to get P power. And then after we get the polytropic power, there's another formula in order to find the polytropic work, which is W in equivalent to polytropic power over M. M is kilogram per second. So W in for P4 of 2.5 bar is 33.101 kilojoule per kilogram. Same goes to the 4 bar. We obtain the polytropic work, which is W in is equivalent to 88.1769 kilojoule per kilogram. And then for lastly is 7 bar. We obtain the calculation. We obtain the polytropic work, which is 141.0208 kilojoule per kilogram.
What is the polytropic efficiency of air compressor? Question number 5. Calculate the volumetric efficiency. First, you need to know the formula for efficiency motor and efficiency pump. Next, you need to have the value for P4, PE, efficiency motor, and PP. And then you need to find the PS, value for PS, and then you need to find the value for efficiency motor, which this formula. It is volumetric efficiency formula. You need to find the unknown in this formula. For the example, for this calculation, we take the 25 bar. You need to find the epsilon for first stage and the second stage. For the first stage, P1 per P0 is 7.5, and this is the value efficiency formula. And when you have the unknown value, you just insert and you get the answer. The first stage efficiency is 65.19%. The second stage, P2 per P1 is 1.39, and you insert the unknown value in this value efficiency, and the answer efficiency for second stage is 98.71%. Question 6. Based on the value n at question 7c above, the volumetric coefficient n for a two-stage air compressor was depending on the coefficient value at 25, 4, and 7 bar. Unlike the thermal process, adiabatic process only release energy in the form of work to the environment. In term adiabatic alternative refer to heat transfer technique. Heat can flow with the environment is an exothermal system while maintaining a constant temperature. You need to find the Q1 and Q2, and this example is for 2.5 bar. You need to find the value for M1 and M2, and then you need to do the interpolation for certain temperature to find the value for hash. T7 29.8 Celsius, and after you do the interpolation, you can get the value for H7. Here for the example for the interpolation. After you get the value, for Q1 and Q2, and you have the adiabatic efficiency formula. Q1 minus Q2 per Q2 times 100%, and for 2.5 bar efficiency, adiabatic efficiency, and this is the value for Q1 and Q2. You insert in the adiabatic efficiency formula, and after you calculate, you can get the answer is 88.6% adiabatic efficiency for 2.5 bar. This is the pH diagram for these two-stage compressor, and this is the flow for the two-stage compressor, and mud and block for in this point for the two-stage compressor.
Conclusion. Throughout this experiment, we can conclude that the objective of the experiment was achieved, which is to understand the polytropic process and the performance of the two-stage compressor. Recommendation. Students need to understand the procedure before run the experiment to improve the accuracy. Correctly read the pressure value from the gauge. Make sure P3 is stable when the reading of the gauge.